Okay. Here it is. All right. To my Chem 100 class. I forgot to start the recording. So that means I'm here after class going through the entire review process again. So what I'm going to try to do is to retrace my steps, but the problems that I'm working out for you and trying to answer the questions that you posed during the class period, I'm trying to recreate that in the form of worked problems, but they may be out of order, in a different order than we encountered them in class. But I might also add that there is a recorded video of a review session on Blackboard for this class, but it was one that I made in the spring with the Chem 100 class. So if you look at that one, you might see a different set of problems being worked. And it may be of some value to go and look at both of these videos before our test on Thursday. All right. So as I recall, I started out with describing a gas. How do we describe a gas? What are the 4 parameters that will completely describe a gas and from which we can derive some of the gas laws? So those 4 are pressure, volume, temperature, and moles. And for many applications, not all, but many, pressure is going to be in atmospheres, volume is going to be in liters, temperature, however, is always in Kelvin. And then N, of course, is my abbreviation for moles. Okay, so the gas laws that we have so far are Boyle's, right? And Boyle's law addresses the change of pressure or the effect of pressure on the volume of a gas, and that's equal to a constant value. Now, because this is a product equal a constant, this is a direct proportion. In other words, if it's constant, if the product is constant, then whenever pressure goes up, volume has to go down. So in that case, pressure and volume are allowed to change, which means that temperature and moles must be held constant. The next, in historical terms, is Charles' law. And in this one, Charles investigated the effect of temperature upon the volume of a gas. And this is incorrect. It's not a direct relationship. It's an inverse proportion, which means that one goes up, this one goes down. When a quotient is equal to a constant, then you have a direct relationship, or a direct proportionality. So if we're going to let volume and temperature vary, then we have to hold pressure and moles constant. The next one, historically speaking, is Avogadro. And for Avogadro's law, Avogadro investigated the change of volume with respect to a change in number of moles. And this also is a direct proportion. So if we're going to let volume and moles change, we have to hold pressure and temperature constant. Then there are situations where multiple variables are allowed. And for that, we just need to combine these three laws into one combined gas law. And for that, all you need to do is to note where are these variables located in their respective laws. Pressure and volume are both in the numerator. Temperature and moles are in the denominator. Okay, so there's your combined law. Now, useful forms of these laws. All of these laws can be used in situations where you have before and after conditions. Right? Right? So Boyle's law would be before equals after. Okay? Charles' law would be before equals after. Avogadro's law, before, equals after. And the combined law just combines each one of those into this before equals this after. Okay? Notice one thing about the combined law. If you hold temperature and moles constant, you get Boyle's law. If you hold pressure and moles constant, you get Charles' law. And if you hold pressure and temperature constant, you get Avogadro's law. So these are the before and after conditions. If you know, if you're given in a problem the conditions before they're changed and then some of the conditions after they're changed, then you look to these types of expressions. And if only two of them are changed, I mean, if two are varying, then you look for individual laws. But if three or more are allowed to change, then you look for the combined law. And these are before and after conditions. Now, if you find yourself in a situation, I call it the state law, but it's actually the ideal gas equation. You only know the conditions right now. It's present state. Then you would use this expression, PV equals nRT. We know what PV, N, and T are. R is the constant, the universal gas constant. And the units of the gas constant tell you the units that have to be used for each one of these variables. So since we're only using R equals this value, liter atmospheres per mole K, that tells you that volume has to be in liters, pressure in atmospheres, moles, and temperature has to be in Kelvin. But if you only know the present state, then the ideal gas equation is where you go to find your answer. There's one other law that we dealt with later, and I might as well put it on the board now so we have them all together. But the use of these laws doesn't matter what the gases are, what the gas is, what mixture of gas there is in the container, as long as you don't care what the mixture is. If you want to know something about the mixture, then you have to go to Dalton's law. And that's partial pressures. And remember, the total pressure exerted by a mixture of gases in a container is the arithmetic sum of the pressures of each of the individual gases. Out to however many you have, it doesn't matter how many. You could have 100 gases. It'd be more difficult to get the information that you want with that mixture, but the law still holds. The total is the sum of the individual pressures of each of the gases in the container. Okay, so while I'm here, the difference between an ideal gas and a real gas. When gases were first being investigated, fortunately, the conditions at normal atmospheric pressure and room temperature were such that ideal gases and real gases behaved virtually identically. There was no difference. So, and that's fortunate because all of these laws are developed with the ideal gas in mind. In other words, every gas behaves like every other gas under these conditions, and that is true. These conditions happen to be high temperature and low pressure. Now, the question should be in your mind, what do we mean by high temperature and low pressure? High temperature is relative to 0 Kelvin. So 273 degrees Kelvin, which is standard temperature for gases, is a high temperature. Low pressure is relative to something like 100 atmospheres. That would be high pressure. So at 1 atmosphere and room temperature, 0 degrees Celsius, or even 25, whatever, high temperature and low pressure conditions are met, and ideal gases studied under these conditions, real gases, excuse me, studied under these conditions behave as if they're ideal. So what makes an ideal gas? Well, we have assumptions. The assumption is that there are no interactions. Between the gas molecules when they collide with one another. They don't attract, they don't repel. In fact, these conditions are part of the kinetic molecular theory of gases. They don't interact. They just act like billiard balls when they bounce off each other. And in fact, we prefer to think of them as not even being there. They don't exist. The gas is there, yeah. It occupies space, but we treat it as if the molecules aren't there. And under conditions of high temperature and low pressure, that's virtually true because the distances between gas molecules are huge compared to their individual volumes. So there are no interactions, and they bounce off each other like billiard balls. And the way we assure that that will happen is that under low pressure, there are not that many gas molecules in there to start with, right? So you have few interactions. And at high temperature, we give them such a huge amount of energy in terms of their velocity that when they do bounce off of each other, there's neither time nor inclination on a molecular level for them to interact. Okay, so let's go to specific problems. As soon as I erase this board. I'm going to leave these conditions here just for reference. And let me look at our problem set and see if I can recall which ones we did. And in roughly the same order. Suppose we look first at number 1. Right? So we have 2 balloons. They're both at the same temperature and they're the same size, which means what? Volume. So the 2 balloons have the same volumes and they're at the same temperature. What about pressure? Problem doesn't say anything about pressure. We have to assume that the pressure is the same because you're not told that it changes. One balloon contains hydrogen and the other contains carbon dioxide. And a little blue smoke is thrown in there. This one floats in air, this one sinks in air. So what does that mean? That just means the densities are different. So the density of this one is not equal to the density of that one. Which balloon contains a greater number of molecules? All right, there's the question. Which one contains the greater number of molecules? Well, actually, if you look at the possible answers, you'll see that that question is misleading. The question is assuming that there are different numbers of molecules in each one. But if we go to Avogadro, Avogadro said that if these conditions are equal, this one is equal. The number of moles of each is exactly the same. Now, Avogadro's proposal that these moles were the same was a pivotal point in the history of chemistry. There was a conference in Karlsruhe, Germany, at the university there. This is in southern Bavaria. And all the great minds and chemists in Europe were there. They met there in 1865. And their purpose was to find out, try to deduce, try to get some insight as to what was going wrong with their chemical reactions. So why was it going wrong? Well, at this time, the only thing that the chemists understood was mass relationships in a reaction. They knew that when you added 2 or more things together and they reacted, you ended up with something different, but the masses were equal, both sides. They knew that for sure. They just didn't know why that was true. The concept of numbers reacting, and in terms of moles, as we know it today, the mole ratio, the mole relationship of reactants and products was unknown. So, how did Avogadro solve that problem? Well, he did so indirectly. He got credit for it because he came up with the idea originally. But the person who was responsible for changing everyone's minds at this conference actually didn't change their minds during the conference. Everyone just threw up their hands and left the conference after 3 or 4 days because they couldn't figure it out. So there was this young chemist, see if I spell his name right. Maybe that's right, Cannizzaro. His work was based upon Avogadro's. And he gave Avogadro credit, like any good scientist would. And he was handing out reprints of his published paper as everyone left the conference. So they took these papers back to their respective universities and companies and read the papers, and the light bulb started going on all over Europe. Now they understood that if they had equal conditions of volume, temperature, and pressure, they knew that the number of moles of the gas in each container would be exactly the same. It didn't matter what gas it was. So if you had a gas here of one type and a gas here of another type that were going to react, and you had the conditions exactly the same, you knew that you had equal moles of each one going into the reaction. Or you could measure the outcome and know the equal moles, even though the masses would be different. If you know the moles are equal, then when the masses change, you knew that the mass difference was due to the mass difference of each individual molecule. That's when they knew how to approach these problems from a mole standpoint rather than a mass standpoint. And then the relationships of mass to mass were obvious, and they solved problems right and left. Universities started publishing papers like crazy. Companies were making money hand over fist because they could solve their engineering problems in the process of production and lose no money or less money in the process. Their engineers were making them money. And therefore, quite a few years, Germany was the place to be if you were a chemist. In fact, most of the papers in the world were published in German, and if you wanted to be a chemist, you started in high school learning German. Okay, so that's problem one. Let's see what came next. Let's see here. How about number 5? I think we did that one next. So number 5, you transfer a gas that initially is at 25 degrees and 2.49 liters and 0.95 atmospheres to a new vessel at 32 degrees and 8.75 liters. You want to know the new pressure. So what kind of problem is this? You're given before conditions and after conditions. Obviously, you need one of the original gas laws or the combined law. So which one would it be? Well, which conditions are changing? You have an initial temperature of 25 degrees. You have an initial volume of 2.49 liters. And you have an initial pressure of 0.95 atmospheres. There we go. And then you let it change. So what are the new conditions? Well, the new conditions now are 32 degrees and a volume of 8.75 liters, and the pressure is the unknown. So by setting up your problem this way, what do we know? You can tell that we're going to have three variables changing. And none of the individual gas laws will satisfy the conditions and answer the question. So what you need here is the combined gas law. But you don't need all the terms, right? Because we quantitatively transferred that gas from one vessel to the next. That means the moles are the same for both sides. That means this term drops out and you're only left with PV over T equals PV over T. Now all you have to do, since you laid it out this way, you know which terms are before and which terms are after. And there's no way you can make a mistake putting these numbers into the wrong place in your equation and obviously getting the wrong answer. So the pressure is going to be 0.95 atmospheres to begin with. The initial volume is 2.49 liters. The temperature is what? The temperature needs to be in Kelvin. Right? So you have to add 273 to it. Then the after conditions. This is our unknown. And volume is 8.75. And the new temperature also has to be converted to Kelvin. There you go. Your problem is set up. Solve for the unknown. So if we solve for that unknown, there we go. Notice also that the only units that we had to be absolutely sure were correct was temperature. Temperature must be Kelvin. But the others, atmospheres, liters, it could have been torr here instead of atmospheres. Then the answer would have come out in torr, values of torr. Liters, it could have been milliliters on both sides. It doesn't matter. The only one that matters is the temperature. And that holds true for these ratio equations, the before and after types. The only one you have to be concerned with is temperature. And of course, what units are the answer to the problem of your multiple choice problem. Right? If you came out with torr and the answers were all in atmospheres, you would have to change, right? So how would you change atmospheres to torr? You need a conversion factor. 1 atmosphere is 760 torr. So 760 times that will give you the value of torr, or millimeters of mercury. And there are other conversion factors that are in your review document in the back in useful information. So if we had to convert that to pascals, we could do that too. But the problem at this point is essentially solved. So that was number 5. And that was a before and after type problem. So let's look at a different one. What if we do no, that's a before and after. I want to do one that is a little bit different. Indulge me for a moment. I'm at number 41. Okay. This problem says a sample of oxygen has a volume of 7.08 liters at a temperature of 19 degrees centigrade and a pressure of 1.38 atmospheres. Calculate the number of moles. So what type of problem is this? Are you given before and after conditions? Nope. You're given conditions of the gas in its present state. So what are the conditions in the present state? Well, it's oxygen gas, but does that matter? It doesn't matter one little bit. A gas is a gas is a gas, as they say. So volume equals 7.08 liters. And by the way, well, let's put down what we know. Yeah, let's get what we know first. Temperature is 19 degrees C. We know we're going to have Kelvin, so we might as well convert it now. Okay, and we're also given pressure. And the question is, how many moles? So if this is a state function, the equation you go to is the ideal gas equation. And R is going to be what? That's the ideal gas constant. And that tells you the units for each of the other values. Liters, volume, correct. Atmospheres for pressure, correct. Moles, that'll be our answer, and K for temperature. So we're good. Now we can solve this for moles and substitute our values. And temperature. So let's see if I get the same answer as the answer key. I'm going to find my calculator. All right, 1.38 atmospheres, 7.08 liters, gas constant, and temperature. And I get 0.408 what? Moles. So let's see if that's the same answer that's in the key. Yes, it is. For 41, that's A. So this is a problem that requires a state function. In other words, that equation. And for that equation, you have to be absolutely certain that your units are proper. It's not like a ratio where you can use any unit you want except for temperature. In this one, you have to use the units that are common to the constant. Okay, that was 41. So let's do a couple of thought problems. Ones that don't require a lot of math. Well, maybe one of them does, but it's more of a theoretical type problem. So let's look at number 7. Right? So we have 4 balloons, and each one contains 6 grams of a different gas. So we have 6 grams of each one. And from the answer choices, we know that those gases are this one, helium, krypton, and neon. Now, the problem implies that all the conditions here are the same except for volume. And then the masses are equal, the pressures are constant, temperature is constant, the volume is going to change. Constant, volume change. So, if we're going to let volume change, the only other thing that can change is the number of moles. Right? So we're actually looking at Avogadro's law. So if they have equal masses, what does that say about the number of molecules or the number of atoms in each balloon? What it says is that if they all weigh the same, the question is, does each one of these molecules or atoms weigh the same as individual particles? That's the question. If each one weighs the same and they have the same mass, then they're all going to be the same volume because you have the same number in there. But do we have the same numbers of molecules in there? The answer is no, because we know now that each one of these weighs something different. Nitrogen is going to be 28.02 grams per mole of nitrogen. Helium is going to be about 4. Krypton is a monster, 83.80. And neon is 20.18. All right, we know that each is different. The question is, which one has the greatest volume? Well, the greatest volume is going to be the one with the greatest number of moles, right? Because this ratio is equal to a constant. So if the number of moles goes up, the volume goes up. Then the question becomes, if we want to answer this question, we need to know the answer to this question. How many moles of gas are there in each balloon? Well, we could do it quantitatively and just change each of these to moles and then compare the numbers. But we don't have to, because the question is which one has the most number of moles? Consequently, which one has the greatest volume? Well, the one that weighs the least, right? The one that weighs the least is going to take more moles of that gas to give you the same mass, right? So it would take more helium molecules, atoms, to give you the same mass as krypton or neon or nitrogen. So the answer is this one has the greatest volume because it has the greatest number of moles. That was number 7. Okay, so let's do another theoretical. Number 9. This one, I can't imagine how to solve this one easily. My mind just doesn't work around this one unless we use algebra. That's the only way I can solve this problem. So we're given conditions for a gas before and after, right? So that means we need the combined gas law, because why? We're changing the volume, we're changing the moles, we're changing the temperature, and we want to know the effect on the pressure. So we're changing three conditions, and we want to know how the pressure before and after are related to one another. So that means the combined law. So what does that mean? Well, we're going to have beginning pressure, beginning volume, beginning temperature, and beginning moles. And we're going to have final pressure, volume, temperature, and moles. So little zero means initial. How does it start out at condition or position 0? And then final is how does it end up? All right. So let's see what we're given. You double the volume. So that means the final volume is twice what the initial volume was. This one is equal to twice the initial volume. You double the number of moles, right? So the final is equal to twice what the initial was. And you double the Kelvin temperature. So the final temperature is equal to twice the initial temperature. This is the question. How is that one related to this one? Okay? So, what do? Well, we set up the combined equation, PV over NT initial is equal to final right? And then we solve for the unknown. We want to know what relationship is PF. And if you look at the problem, the last symbol in the problem before your answers is PF equals. So we want to know PF equals what? And we're looking for PF in relation to P0. So let's solve this equation for PF. Right? So PF is held here. These two go over there. P0, P0, NF, TF. And this one comes over here. N0, T0, VF. Okay, so now we've solved for this one. We need to substitute in here so that we have left over only that one. So let's say the initial values are off limits. You don't mess with those. We want to know what are the finals in terms of the initials. So in order to do that, we're going to say P0, V0 over N0, T0, and then substitute in what's N sub F. N sub F is 2N0. Right? T sub F is 2T0. And V sub F is 2V0. There. Now we have an expression for P sub F, and notice what happens. We get to cancel, right? A variable, a number divided by itself is equal to 1. A variable divided by the same variable is also equal to 1. So that, in other words, and another way of saying that is they cancel. So moles cancel, volume cancels, temperature cancels. And what are we left with? We're left with this term, that number, and that number. So if we want this in terms of that, what's the number in front of P0? Well, it's 2 times 2 divided by 2, which is what? 2. So the final pressure is equal twice the initial pressure after these changes have been introduced into that system. All right. Now, let me see. I think the next item we had covered was a stoichiometry. Right. So let's go back to number 6. I think number 6 was one that we covered for stoichiometry. So let's read the problem. When acetylene gas burns, how many liters of O2 at STP are used for every 9.31 moles of acetylene burned? Hint, write the balanced equation for the reaction. All right. So maybe you don't know this, but when you combine a hydrocarbon with oxygen and you burn them, you ignite them, right? Anybody that's used an oxyacetylene torch knows that it burns with intense heat. So it's exothermic, produces carbon dioxide and water. And if we're at STP, that's liquid. So you may not know this. Anytime you burn a hydrocarbon, you get carbon dioxide and water. So during the exam, if you run into a problem like this, it's fair for you to ask me what the products are, because there's no way you can know that unless you just memorize what I just told you. And that's fine, because it's a good rule to know. Anytime you burn a hydrocarbon, you get carbon dioxide and water. In fact, if you burn a carbohydrate, right, in your body or in a spoon, you can light it on fire. Sugar is a carbohydrate. Starch is a carbohydrate. If you burn those, whether outside the body in a flame or inside your body with the intervention of enzymes, you get the same products, carbon dioxide and water, for both of those types. So what do I mean by carbohydrate? Well, carbohydrate has carbon, hydrogen, and oxygen together, right, in a specific ratio. But that doesn't solve our problem. What we need now is a balanced equation, right? So how do we balance this equation? Well, if we use the method, our budget method, we have carbon, hydrogen, and oxygen in this equation. That's it. So initially, we start off with 2 carbons, 2 hydrogens, 2 oxygens, and we end up with 1 carbon, 2 hydrogens, 3 oxygens. Okay? So what rule do we follow first? We don't touch single elements. Save them for last. Why? Because if you have to put a coefficient in front of this one, it only changes that one. It doesn't change anything else. So you save that one for last. So let's go to the one that needs to be changed first. Since oxygen is off limits, we'll go to carbon. So we need 2 carbons on this side. What does that do to the others? Well, it makes 2 carbons, but it also makes 4 oxygens plus 1 is 5. Okay? Hydrogen's still good, so let's fix oxygen. So how do you get 5 oxygens out of an O2 molecule? Well, look at it this way. Well, it's actually like that. Lone pair electrons. Don't worry about that. When you have these 2 oxygens together in the molecule, how do you get 5 out of 2? Well, if you took 5 of them, how many would you have? 5 times these 2 would be 10 oxygens, right? 10 oxygens. So you need half of that many. So let's say we take half of that many, right? So 5 times 2 is 10, divided by 2 is 5. Right? So if we put 5 halves, that gives us 5 oxygens. Now, technically, we're balanced, and we could solve the problem here, but we want to stick with convention. And what does convention say about balanced equations? Convention says you can't have a half a molecule, right? It's a whole. You don't have fractions of molecules and atoms. So how do you get rid of that fraction? Well, we've got the ratio 1 to 5.5 to 2 to 1. As long as we maintain that ratio, the equation is balanced. So let's just multiply the whole thing through by 2. So 2 times a half is 1, right? So that leaves 5 behind. So here's our new balanced equation. 2 times our acetylene plus 5 times our oxygen yields 4 carbon dioxide plus 2 waters. Now our equation is balanced. Now we can go to the next step. What are we given? 9.31 moles of acetylene. Okay? What's the question? How many liters of oxygen? So the question is volume of oxygen. Do we have enough information to answer that question? What would we need to tell us the volume of oxygen? We would need to use our state function, right? If we use this one, that has volume in it, because we definitely don't have a before and after. We want to know how much of this is consumed in the burning of 9.31 moles of acetylene. So what do we need to know to find that value? Well, what else are we given? We're given standard temperature and pressure, which is what? Standard temperature for a gas is 0 degrees, and pressure is 1 atmosphere. Right? So we've got this one, because we're going to change it. Right? We got this one because it's a constant, and we got this one. Right? So, do we have enough information yet? Well, almost, right? So we've got 2 variables here. We can't solve that equation yet. We need only 1 variable. So can we find one of these variables? Let's go back to the question. They want to know what's the volume, right? So if this is going to be the unknown, we've got to find out what that one is. Can we find out what that one is from the information given? The short answer is yes, because we know the number of moles of acetylene being consumed, and we have a balanced equation. We can determine how many moles of oxygen are required. It's a simple conversion. That many moles of acetylene will convert into oxygen using the coefficients 5 and 2. Okay? So if we take 9.31, multiply it by 5, and divide by 2, we get 23.28. Moles of oxygen. Okay, now we have that one, and we can find out what the volume is. All we have to do is solve for volume. Oops. and fill in the numbers. So how many moles? Well, 23.28. I'm going to leave the units out because it gets messy. We already know that our units are correct. And pressure is 1 atmosphere. So the volume is calculated from those values. And I get 52.1 liters. Let's see if that agrees. Nope. Because I did it wrong. There. And the closest one to that one is, I know what happened, the rounding error. I used a different value for this one before I rounded it. So the answer is 522 in the problem set. Right. So that's what you would look for. Just a reminder, in a multiple choice test, if you can't find the exact answer you calculated, pick the best answer. Okay, that was number 6. All right, let's see. What do we have next? That was a stoichiometry problem, which is a good one. I think I went way toward the back. Oh, here's another one. Okay, I think we did do this one. Number 39. Zinc metal is added to hydrochloric acid to generate hydrogen gas is collected over a liquid. We'll go ahead and do this one. So zinc metal is reacted with hydrochloric acid to produce this salt. Actually, that's aqueous. And hydrogen gas. So to balance that one, we need 2 here, 2 here, and 2 here. Okay. You don't have to do that to answer the question, because the question says you collect that gas from this reaction vessel in a container of water into which we have submerged or inverted a collector of some kind that's closed at this end, and it's filled with water to start with. All right, so we're going to have little bubbles coming up from this reaction. Now, what is collected in that vessel? Hydrogen gas plus what? Water vapor. So that plus water vapor is collected in the container. All right, now we're given some other information. Well, actually, it doesn't say that this liquid is water. It just says the vapor pressure in there is the same as water at 20 degrees. And we're told that the partial pressure of the, let's be consistent here. This is a liquid. This is a some vapor plus hydrogen. So this vapor pressure at 20 degrees centigrade is 18 torr. Okay? The volume of the mixture is 1.7 liters, and the pressure is 0.788 atmospheres. What are the number of moles of hydrogen gas present in the sample? All right, so where do we go from here? Actually, there's a lot of blue smoke here. All you need to focus on is pressures. This is the total pressure. This is the partial pressure of the vapor, and the partial pressure of the hydrogen is equal to the total plus that vapor. Oops. So if this one is 0.788 atmospheres and that one's torr, we want to know what the units of measure are. Look at the answer. Well, actually, this wasn't the problem we answered, but it's a good one. So let's continue. The number of moles of hydrogen gas. Okay. We have a volume here, total volume. We have a total pressure. We have a partial pressure. So we have pressures taken care of. We have a volume, which is equal to 1.7 liters. And we have a temperature of 20 degrees. And the question is moles. So this is a state function. We're going to find out how many moles. But we don't want to calculate the number of moles of all the gas. We just want the number of moles of the hydrogen gas. Right? So we need to remove the pressure of the vapor from the total so that we're only dealing with the pressure of the hydrogen. So if we take this one and convert it to, now let's do it the other way. We're going to need atmospheres. So let's convert this one to atmospheres. 760, right? So 18 divided by 760. Is 2.368 times 10 to the minus 2. Atmospheres. Right? No? 368. My dyslexia kicked in. Okay. So let's see. If we're going to have 0.788 atmospheres total, and we're going to subtract this one from that one to get this one, let's put this one in standard notation. So 2 places, 1, 2, 0, 2, 3, 6, 8. And subtract that one from that one. So I get 0.764 atmosphere. Now we can solve for the number of moles. So the pressure is what? The pressure of hydrogen gas. That's the pressure of hydrogen gas. 0.764 atmospheres. Volume is 1.7 liters. R and temperature. Okay? So I get, let's see, what units are we given here? Standard notation. 5.4 times 10 to the minus 2 equals 0.054 moles of hydrogen. Okay? That was not the same problem we worked earlier. It was similar. This one was a little more complicated. But it used Dalton's law of partial pressures, along with the ideal gas equation. So the question was asked in class, how do we know which formulas to use? You use the formulas that you need to use to answer the question. I know that sounds like a cop-out, but the only way you're going to know which equations to use is to work lots of problems, lots of different problems. And as you proceed, you think about what type of problem is it? Is it just a simple, straightforward before and after calculation? Great. Those work. Is it a state function? Do I know just what it is right now? Then use the ideal gas equation. But if you combine it with some other, right, then you've got to mentally break it into pieces. And the one question may actually be 2 or 3 or even 4 questions that need to be answered in sequence to get you to the answer. So it's helpful to work these types of problems from the backwards forwards. Because if you work them backwards, then you know, all right, this is the answer I need. That's where I need to be. How do I get there? Well, if I had this information, I could answer that question. Okay, if I need that information, do I have it from prior information, right? So you may have parts of it, but you have 1 or 2 items that need to be answered. So you go up here and say, can I answer that one from the information? Turns out usually you can, especially if it's on an exam. You're going to be given enough information. Or you may have to go look for the information, right? For instance, on the periodic table, or in the chart of useful information at the back of your exam. But this is part of the reasoning process, and it's one of the hardest things for students to do, to synthesize the information that you've given, the rote learning that students are prone to do, and take that and mix it together in the right proportions to give you the answer. And that only comes from practice. Work lots of problems, lots of different problems. And eventually you develop an intuition for how to approach a different problem. Let's think about it. In the real world, things are not in neat compartments like gases. Okay, we're going to do a gas problem here. Usually, you've got gases, liquids, solids, all mixed together. And what you have to do is tease the answer out of that information by using what you've learned about the individual compartments, right? That's just a method for learning. Solving the problem requires that you synthesize everything that you've learned back here, bring it together, and say, all right, what type of problem is this? Well, if it's not a pure gas problem, maybe there's something else involved, like this reaction in which did produce a gas, but it started out as a solid and an aqueous solution. Right? So there's really no easy way around working lots of problems. And you know my motto, actually it's in the form of a statement. If you're not bored stiff working chemistry problems, you haven't worked enough of them. So what does that say about me right this moment? Right? Doing this right here, I am bored to tears. And you should also be bored in the process of working these problems. Okay, so enough of my soapbox. Let's go to, what other types of problems can we do? We'll move closer to the final pages. All right, let's take a break. Let's take a break from this heavy brainy stuff and just see if we understand something about the gas laws and how they look on paper. Which of the following will give a graph with a straight line and a y-intercept of 0? Number 49. So we have these possibilities. A, volume versus temperature in degrees C. B, let's see, let me move this down some. So we have to draw a graph. B, volume versus 1 over temperature in Kelvin. C, volume versus temperature in Kelvin. And D, volume versus 1 over temperature in degrees C. Which one of those will give you a straight line with a y-intercept of 0? All right. So what do we know about volume and temperature? Right? As the temperature increases, this was Charles' law, right? The volume would increase, right? So it'll be a straight line, but where is that straight line positioned if it's degrees C? Remember all those different gases on the one slide in the PowerPoints? Some of them went like this, some went like that, some went like that, that. But where did they all cross the y-axis? Up here, right? None of them went through the origin. We want the one that goes through the origin. So how do you get it to go through the origin? You change the temperature scale. The temperature scale of degrees C can be positive or negative, right? So these may intercept the 0 volume out here somewhere. The way we get it to go through the origin is to move all of them down like that, to where they all go from here. 0, 0. But the only condition under which that happens is if the temperature is in Kelvin. That's why we have to change temperature to Kelvin every time, because we want it to go through 0. That's the origin. So that means that this one is our answer. Volume versus temperature in Kelvin will send you a straight line through the origin, because there's no such thing as a negative K. There's no way that it can intercept up here, because that would be a negative K temperature, and they don't exist. So they have to go through 0 or anything above it But as it turns out, all gases plotted this way originate from 0, 0. Okay, I don't think we covered that one in class, but that's a good one. Let's see what else I can find. Okay, we did that one already. Let's look at, let's go toward the back. I think there were some high numbered ones back here that we dealt with. Ah, yes, here we go. Let's see, I did one before that. Yeah, I did 78, but we talked about 78 earlier. 78 was just answering the question, under what conditions is a real gas like an ideal gas? And that's under conditions of high temperature, low pressure. That's it. If you're going to memorize something, that's a good one to memorize. Now let's go to 81. I know we did that one. There are two approaches to this one. Well, let's first, what's the conditions? What's the question? Determine the molecular formula for this hydrocarbon. So we've got a hydrocarbon. It has some formula, a ratio of carbon to hydrogen, right? We want to find out what that is. What information are we given? Well, we're told that a 15-gram sample is placed in a balloon at 1 atmosphere. So the mass is 15 grams. Pressure is 1 atmosphere. Temperature is 25 degrees C. Might as well change it already. That's 298 K. And a volume of 12.2 liters. So that's our given information right here, except for the composition of the compound. So here's the composition. 79.89% carbon, 20.11% hydrogen. Now, if we use our convention, we would assume in order to convert this to moles, because we have to have moles if we're going to have a molar ratio, which is basically what that is. Number of carbon moles to number of hydrogen moles. You can't convert a percent because it has no dimensions. It's just parts per 100. But if we have 100, how many grams of each one of these do we have? Aha, now we can convert to moles. So carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. Right? So now we can find out what that ratio is. 79.89, 12.01. So that's 6.65 moles of carbon for every 19.91 moles of hydrogen. So now we just have to convert it to a whole number ratio. Right? So we divide everything by the smallest one. That's 1. And this is going to be 3. Check it on your calculator. So that gives us the empirical formula. 1 carbon, 3 hydrogens. But we want the molecular formula. So what do we need to know to give us the molecular formula? we need a multiplier. Right? How do we find that multiplier? Well, we need, what's the ratio of this formula to the actual formula? Right? So how do we find that? Well, we have a molar mass for this one, I call the empirical weight. So that's 12.01, and 3 times 1.01. Right there, grams per mole. Right? So what we need is the molar mass of the compound itself. Can we determine that? Well, we have the mass, right? And molar mass or molecular weight is mass per moles. We have the mass, right? Grams. We need the number of moles, right? So how do we find the number of moles? It's a state function. What is it right now? Right? The number of moles is N equals PV over RT. Pressure is 1 atmosphere. Volume is 12.2. 0.08206. And temperature is 273. Right? So what do we get for the number of moles? Let's see. I get 0.545, 0.545. 5 moles. So now we have the moles, we have the mass. Divide that value into 15. And we get 27.5. Is that right? Let me see if I did something wrong. I did something wrong. Ah, I know what it is. Temperature. Point 0.08. Oh. Did I use the wrong value here? 0.08206. I think I punched in the wrong value. Try this one again. 12.2, 0.08206, 273, yeah. 0.08206, 0.8206, 25 and 273 is, that's, 8, 273, 8. There's the problem. $535. Okay. There we go. 0.535 divided into 15. I get 28 grams per mole. All right. I'm still not where I wanted to be. Two. One more time. My class needs to be here. Catch me making these boo-boos. So round it off. There. 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 All right, now it makes sense. So if the molecular weight is 30 and the empirical weight is 15, what's the ratio here? X equals 2. So the formula is C2H6. All right. Let's see what other mischief I can get myself into here. Let's back up. Oh, I did 79, didn't I? 79. We did that one. So let's look at this one. For 79, what are we given? What's the question? What is the molar mass of the compound? So we want the molecular weight is mass divided by moles, grams per mole. Okay? But what are we given? We're also given density. So what's density? Mass per unit volume. And we are given, well, here's the mass part, there's volume. We need moles. So what do we know that has moles in it? Well, since we're given these values, 1 atmosphere pressure, 145 degrees centigrade, and whatever else we're given is a little bit different. But we're also in need of some way to calculate moles, right? So let's take this equation, these three equations, and see if we can derive something that will give us molecular weight. Right? So let's put what we know. So we've got a temperature of 145 degrees C, which is what in Kelvin? 273, that'd be 418 K. We're also given pressure, 1 atmosphere. And we're given density of 2.45 grams per liter. Okay, now, we always want to, the question is solving for molecular weight. So this one always has to be by itself. But if we solve this one for mass, right, we can substitute that in here. So molecular weight then would be D times V divided by moles. Okay. Then we need something to substitute for moles. Right? So if we solve this one for moles and substitute that in here, we have density, volume. We're keeping density and volume. Density. We're also given volume too, aren't we? No, we don't need volume. I'll show you why. So this is divided by that one, PV over T. And notice in algebra, the denominator of the denominator is a numerator. So it's d v r t over p v. And the volumes cancel. So now we have density times gas constant times temperature divided by pressure equals the molar mass. So let's plug in our values. Density is 2.45. Gas constant, temperature, and pressure, 1 atmosphere. Now, if you do that calculation, let's see, where was I? 79. If you do that calculation, you should come up with grams per mole. Okay? Let's see what else. I'm trying to think of something that I may have missed in the class time. That I could bring out now in this rerun. How about this one? This is a thought problem. Just to drive home another point. So let's look at 23. You're playing with a helium balloon on a typical warm California day. And maybe so, maybe not. Depends on what part of California you're in, right? Suddenly the Celsius temperature doubles. Which of the following is true? So you got a balloon, and the answers talk about volume and pressure. Okay, so you got this balloon. Moles are going to be constant. Right? It's got a certain number of moles in it. Temperature changes. So what happens? Well, what happens to the temperature? Well, the final temperature is in degrees centigrade is twice the initial temperature in degrees centigrade. Okay? That's the key right here. So if we're going to talk about gas laws, what temperature do you have to have? Kelvin. So what does this look like? Well, if the temperature final is this, degrees C final, K final. Let's substitute in for these values what they would be in Kelvin. So if this degree C is some value, let's say TC. So this one will be 273, right? And this one is twice TC times 273, plus 273. Now notice, has the temperature actually doubled from here to here? No. It's crept up just a little bit. Let's use a real temperature. Let's just say standard temperature. So if the temperature starting is 0, then your temperature went from 273 to, that's not even right. It went from 273, now let's use a real temperature, 20 degrees. If you start at 20 degrees C and you double it, what do you end up at? 40 degrees. All right. Now, what's 20 degrees in Kelvin? 293. And this one is 20 plus that, which was the 313. Okay. So from 293 to 313, have you doubled? No, you have not doubled. Right. So now we can answer the question. So A says the actual temperatures are needed to answer the question. Do you need the actual temperatures? Well, we used an actual temperature, but you don't need it. You don't need the actual temperatures to answer this question. The volume of the balloon will slightly increase. Is that true? If you increase the temperature and the pressure stays constant, then the volume should increase, right? They're direct proportion. So this is true. The volume will increase slightly. Notice we didn't say it would double. If the Kelvin temperature had doubled, yes, the volume would double. But the Kelvin temperature did not double. It only moved up slightly. So the volume would increase slightly. We know that was true. So the rest of them, the pressure inside the balloon will double. No, the pressure is not going to double because you did not double the temperature, right? And the relationship between pressure and temperature is also direct. So that was false. And D, the volume of the balloon will decrease. Well, that was just stupid. When you increase the temperature, the volume has to increase. So that was false. And E, the volume of the balloon will double. No, we just said that can't be true because the temperature did not double. Right, so the only one that's true is B. The volume of the balloon will slightly increase. Okay, let's see. I want to be sure I didn't miss any that we covered in class. Oh, by the way, I probably said this at the beginning, but I'll say it again. There's another review video from the spring that covers some different problems. Some of them are the same as these, some of them are different. So it would probably be a good idea to look at both of them because they're working off the same document. It's just that the class in the spring was interested in a different set of questions that were giving them trouble. And if you look at those questions and say, well, that's no big deal, then just go on your merry way. Okay. Oh, here's a good one that we did not do in class. '74. You have a partially filled party balloon with 2 grams of helium. Right, so the mass is 2 grams of helium. There we go. Then you add 3 grams of hydrogen. So the mass of helium is this. The mass of hydrogen is 3. Okay. Assuming constant temperature, temperature is constant, and pressure is constant. Right? So I'm thinking that volume and moles might have an impact here. How many times bigger is the party balloon? Comparing before and after. So we did start off with a certain number of moles, and we added some moles right here. So then the volume is going to change, but we need to know how much. Choose the best formula to use to solve this problem. Okay. So look at what we've got. Well, we've got before and after, right? We've got before, and then add makes after. So since we're letting several things vary, actually we're not letting several things vary, but in order to find out which formula to use, it's probably a good idea to start with the combined formula and then cross out the ones we don't need, or the ones that are constant. So let's start with before equals after. Okay? So if temperature and pressure are constant, right, these go out, and that leaves volume divided by moles. Okay, that's good. Volume 1 divided by moles 1 is volume 2 divided by moles 2. Then, with that being said, look at your choices, right? Which ones of A, B, or C, A, B, C, D, or E? So this one has V2 over V1 equals T2 over T1. This one has P2 over P1 equals N2 over N1. C has V2 over V1 equals mass 2 over mass 1. Volume N2 over N1. And then pressure volume, pressure volume. Okay. So these are our choices. From this place, we see that V1 over N1 equals V2 over N2 would solve the problem. Now, can we say number of moles before and after? Yes, we can, because we have the mass of that gas, which can yield to moles, right? And we have the mass of this one, which can yield to the change in moles, which added together with the original gives us N2. So we can tell how many moles before and after. Before is just this. After is both of them added together after you change them to moles. And then we have volume before and volume after. And the question is, which one is the best formula to do that? Well, pressure and temperature are held constant. So anything that's got pressure and temperature in it doesn't count, right? There's pressure, it doesn't change. There's pressure, it doesn't change, right? Temperature, there's temperature, it doesn't change, right? So it's really a choice between this one and that one. Now, can we say that the volume is related to masses? No. The gas laws say nothing about relationships of volume and masses. They may imply, but you first have to make conversions. So masses don't count. This is the only one that makes sense. V2 over V1. Right. Well, we have to arrange this one, right? So V1 comes over here, and N2 comes over here. There. Now you've got that equation. That was a thought problem, I'm pretty sure. Okay. I think we've covered the problems that we covered in class. And then, of course, if you look at that, that other video from the spring semester, you may see some different problems covered, and so much the better. So I'm going to call it quits for now, and this is the video for fall 2019 Chem 100 on gases. Bye-bye.